This is Brian Putt. A few days ago, a friend of mine asked me about helping him with scheduling a project. In other words, there's a lot of tasks that need to be done, and he wanted to make sure they all got done in time, be able to hold the activity on time. So I set up this little example, which I thought might be helpful for others. Let's assume there are 6 tasks, 6 activities, and they have a relationship as shown here. Task 1 has to be starts, and then task 3 and 2 can start. Task 4 can start after task 2, provided that task 3 is done. Task 5 can start whenever task 3 is done, and 6 has to have both 5 and 4 done. So this PERT diagram shows that relationship. You can also see that relationship here in a Gantt chart, although this is very deterministic, but I'll show you later different options here, how that Gantt chart moves. For each of these tasks, we need to identify a distribution, and typically a triangular distribution is used. You can get fancier, but in the end, it probably doesn't matter because you're adding up these things, although they are correlated in the sense that they have to have one task is a function of the other task being completed. But in any case, I put in some random numbers here, and then sampled these from this distribution, and then use these random numbers and this time to come up with the length of the activity, and put a start date and an end date. Okay. And so if I think about activity 1 with this distribution, it looks like this. It goes from 2 to 4 and somewhat symmetrical around 3. Well, I guess it is symmetrical around 3. All right. So let me show you how this Gantt chart changes with different trials. That's trial 15. And if I go to a different trial, you can see how these are moving around in time. And so overall, when I think about the finish time here, this is the distribution. It doesn't look very symmetrical to me. If I look at the P50 here, it's got more downside than upside as an example. Okay. All right, so we have this distribution. Well, that's great, but what you'd like to know is what activities are critical to being managed to make sure that we arrive on time. Okay. So what things do we need to do? So that's called the critical path. And what we'd like to know is what is the chance that each of these activities is on the critical path. By inspection, we can see that task 1, getting that done, is always on the critical path, because until that's done, nothing else can start. And I can't complete until task 6 is done. So that's almost by inspection, 100% on the critical path. So I think I can do on either one of those to shorten the time would help me get to my goal sooner. But what about these others? Well, here we're going to do something else. What we're going to do is we can establish a reference case. So this is our reference case. And then what we want to do is for each one of these activities, we want to increase the time by just a little bit and compare it to the reference case. So over here on this sheet, I have stored, we have 1,000 trials, and I've stored over here the reference case. So you can see these numbers here correspond right now to over here because I don't have any epsilons over here on my model. These are all 0 here. Now what happens if I put an epsilon We can put an epsilon here, but we know the answer to that one. So let's put an epsilon here. Okay, I'll put 0.01. In other words, the time to complete this particular task, task 3, I'm going to add 0.01 each time. And so now what we want to do is to compare the results, the new results, with the reference case. And so what we see is that in each of these simulations, these 1,000 simulations, they all go up by 0.01. I can then count how many of these are zero, effectively, or not zero. And the answer is 99.7 of them are not zero. So there's just a few that are zero, right? Okay. So what I've done is record that number over here. I've done the same thing for all the other variables here. Okay, I'll put this back to 0 now. And these are the results I get. So I brought these results over here to the model. Okay. So let's look at this. So in 99.7% of the time, I'm on a critical path that says I need to get task 3 done. And then, almost by definition, I have to get task 5 done, because you'll see it's also 99.7 to get to task 6. The other 0.3% of the time, what's critical is task 1 to task 2 to task 4 to task 6. That makes sense? So now I know to focus my management attention on task 3 or 5. So what I could possibly do is either shorten up task 3 or 5, or possibly I could start task 5 before task 3 is completed, or things of that nature. So there may be a multitude of things that could be done, but it's going to be peculiar to the particular situation you're looking at. So I hope you found this valuable, and if you want a copy of this model, be happy to send it to you. Just email me. Thank you.